So I will be doing 1987 M3. So question A is determine the angular velocity bar immediately after the collision. So if we have the center of mass is in the center, then the center of mass will end up at a height of L over 2 when it comes to rest. And if we have our initial kinetic energy plus our initial gravitational potential energy plus work equals our final kinetic energy plus our final gravitational potential energy, and we say our work is 0, our initial gravitational potential energy is 0, and our final kinetic energy is 0, we have that the kinetic energy right after collision is going to be equal to the final gravitational potential energy. So since it is rotating, we have rotational kinetic energy, which is 1/2 I omega squared, and that will be equal to mgh. In this case, h is going to be L over 2. 1/2s cancel out. Then we have to use our moment of inertia equation, which is 1/3 ml squared omega naught equals mgl. We have 1L cancels out, m cancel out, and if we rearrange for omega, we get it equals the square root of 3g over L. And so then we plug in our given values using g is 10 meters per second squared. And the length of the whole rod is our 1.2 meters. And if we plug that into the calculator, we get that right after the collision, angular velocity is 5 radians per second. And since I'm going to clear the screen, I'll make a note of that answer here. For part B, it says determine the speed of the 1 kilogram object immediately after the collision. And so in this case, we can use energy. So we have initial energy before the collision, initial gravitational potential energy plus work equals final kinetic energy plus final gravitational potential energy. No work is done. No gravitational potential in the beginning. So we have initial kinetic energy is going to be equal to the final plus, well, actually, final gravitational potential energy would also be 0 in this case, right before and right after. So we have final kinetic energy is going to be equal to initial kinetic energy. Initial kinetic energy is going to be just the ball, which is 1/2 m v naught squared. Final kinetic energy is going to be both the ball and the rod. So for the ball, 1/2 m v final squared plus, if we remember from the question A, the kinetic energy of the rod just after the collision is also equal to its final gravitational potential energy. So we can make it a little easier by doing mr gl over 2. So 1/2's everywhere would cancel. And then we want to try and isolate our final velocity. So mb v final squared will equal our mb v naught squared minus mass of the rod gl. Then we'll divide everything by mass of the ball and then square root both sides. So we get that the velocity of the ball right after the collision is the square root mass of the ball times the initial velocity squared minus mass of the rod gl, all divided by mass of the ball. And so if we plug everything in, kilogram. Initial velocity 10 meters per second. Squared. Mass of the rod 3 kilograms. Again, G 10 meters per second squared. And then their length 1.2 meters. Divide everything by mass of the ball, 1 kilogram. And so if we plug everything into the calculator, 1 times 10 squared, 3 times 10, we will get that after the collision, the ball's velocity will be 8 meters per second. And again, I will note that here. Then for part C, determine the magnitude of the angular momentum of the object about the pivot just before the collision. So just like in the presentation, its angular momentum will be mvr sine theta. But since the velocity is perpendicular to the radius, sine theta is just 1. And so we can just plug in our values. 1 kilogram, 10 meters per second, and 1.2 meters. We'll get that the ball's initial angular momentum will be 12 kilogram meters squared per second. Note that here. And then finally, part D is determine the angle of theta. And I'll just draw again our R. And so our sine theta is telling us the velocity that is perpendicular to the radius. So in this case, whatever this velocity here is, and if we draw a triangle, this value will be the velocity cosine theta. And so we have to use conservation of angular momentum. So we have initial angular momentum will equal final. Initial angular momentum is that of the ball. Final will be the final angular momentum of the ball, which will be m v final cosine theta, because that's our perpendicular velocity, and then r. Also, the angular momentum of the rod right after collision, which will be I omega. So then we will try to isolate the final velocity, or our theta. Again, use our moment of inertia equation. Then we will divide by our, also we have our mass of the ball here, and our radius. So then we'll divide by our final velocity of the ball, and then we'll do the inverse cosine. So we'll get that theta is inverse cosine of the ball's initial angular momentum minus 1/3 mass of the rod L squared omega divided by mass of the ball radius, and then the final velocity of the ball. So if we plug all that in, we have a 12 kilogram meters squared per second minus 1/3 mass of the rod, 3 kilograms. Length 1.2 meters squared. And then the angular velocity noted 5 radians per second. And then divide all that, mass of the ball, 1 kilogram, times the radius, 1.2 meters, times final velocity, which we said 8 meters per second. So if we plug all of this into the calculator, we will get that theta equals 60 degrees.